jets, explosions, and body interactions, and ionization. All right, go ahead, take it away.
Okay, thank you. So let me start my screen share. Can everyone see my screen? Good. So I work in the general area of star formation. I use APO primarily in imaging mode to obtain images with the Arctic and NICFIPS to measure proper motions over a long time baseline, and also high resolution spectroscopy to measure kinematics. So the background image is a familiar object M16, the pillars, which were ionized by a group of massive stars born about 2 million years ago to the upper right. And in the pillars, there's a half dozen or dozen young stars, including one that's labeled HH216 source, drives a little bipolar outflow. This is just a simple example of the kind of objects I study. Let me start with a bit of an introduction. We've known for decades that young stars and star formation occurs as the gravitational collapse and fragmentation of giant molecular clouds. An image I'm showing you here is the Orion A cloud, which is the nearest region of star formation, where the full spectrum of stars, from brown dwarfs all the way up to massive stars, up to at least 40 solar masses, are forming. The cloud is about 50,000 solar masses today. It was probably about 100,000 or 200,000 10 million years ago. Over the last million years, it spawned about 2,000 young stars, in fact, including the famous Orion Nebula shown in the middle here. And in the background, you see the Orion A molecular cloud. Now, this is only a partial view because to really see what the structure of a cloud is like, you have to look at the full data cube. And so here I show you, registered to the previous image, a slice to the data cube at 3 velocities, color-coded by a Doppler shift at 9, 9.5, and 10 kilometers per second. Our resolution here is about 100 meters per second. This was obtained with an interferometer at California called KARMA, and combined with Nobayama single dish data to recover the full spatial scales in the image. The optically thick 12 CO lines, so only see the cloud surface, near surface, because it's optically thick. If you want to see the interior, you go to 13 CO. And you can see, for example, in M43, just above the Orion Nebula, the dark filament that silhouettes that nebula must be in the foreground of the nebula, because you can see it in emission in these lines. Now, about a decade ago, when we got NICFIPS commissioned, we started looking at the massive stars forming in Orion. Currently, the nearest site of ongoing massive star formation is the Orion Molecular Core 1, about 0.1 parsecs behind the trapezium stars. And in the early 2000s, our NICFIPS images were used in comparison with the earlier 1990s images that discovered the fingers of molecular hydrogen to demonstrate that this, which was the first to be discovered bipolar outflow from any young star in 1976, turned out to be not at all like most outflows, jet-driven. This turned out to be an explosion. In fact, we measured what looks like a Hubble flow in the finger system. What you're seeing here is a combination of NICFIPS H2, molecular hydrogen in red, and iron 2 in the bluish colors. With these images, we propose to use the Gemini South laser guide star system to do adaptive optics imaging. And in the mid part of the last decade, we obtained the following image that shows that the Orion outflow really is an explosion. In fact, proper motions confirmed the Hubble flow nature. And so we started wondering, well, how common are these in the sky? By the way, this proposal also led to an ALMA project, which is still ongoing. And so here's the molecular hydrogen and iron in blue again, and registered to this image as carbon monoxide with 1 arcsecond resolution. And as you blink back and forth, you can see the lower part of the fingers, the inner part of the fingers, show up as a series of carbon monoxide streamers with velocities ranging from -100 to over 120 kilometers per second. Additionally, we learned over the last decade that 3 massive stars, the 10 solar mass Beckmann-Neugebauer object up here, radio source I, which is a 15 solar mass star, the most massive member of this group, and a 3 solar mass star were all ejected about 550 years ago from this location marked by the X, which is the center of the explosive system of molecular hydrogen and carbon monoxide fingers. By the way, that's of course when a light signal got to us. When this event happened, actually, I think Marcus Aurelius was Emperor of Rome. So this was an explosion. Now, this is not common amongst most young stars. Most young stars drive jets and outflows. In fact, In the Orion region, we've discovered hundreds of outflows, including dozens of jets. Now, as a general rule in astrophysics, show me a system that's accreting, spinning, and is magnetized, and then I will show you a jet or a bipolar outflow. That's true for young stars, dying stars, neutron stars, black holes, active galactic nuclei. This is a universal law of physics. And in fact, the Mach number of these flows tends to be related to the escape speed or Kepler speed at the launch point of the jet. Why do we study these for young stars? Because the emission lines that we can study with instruments like Arctic and NICFIPS allow us to learn not only about the morphology, but about the accretion history of young stars. They provide a fossil record of how a star assembled its mass. Additionally, we have learned that these jets trace n-body dynamics in forming systems. And feedback from jets is a powerful self-regulation in star formation. In fact, we think the efficiency of star formation, the fraction of a cloud's mass that can be converted to stars, is limited by feedback processes. So let me show you some examples of jets. So this is an Arctic observation a few years back of twin jets in Taurus. Up in the upper left corner is a binary star that you can't see in the visual. There are two short stubby jets which illuminate this enormous parsec scale complex of shocks in LINS 1551 dark cloud. This cloud is being literally blown out, blown apart by the activity of these jets. The shocks, by the way, with proper motion measurements, range from anywhere from 30 to over 150 kilometers per second. So we can measure this on a time scale of taking images 10 years apart with ground-based images or with Hubble Space Telescope and only a year apart. And I'll show you an example of that. This is another region in Orion called HH24, where NICFIPS shows a complex of jets coming out of a small cluster of stars. In fact, we've recently discovered that there's about a dozen protostars in a very compact group, which are interacting dynamically. And based upon some of this data, we've won a successful Hubble proposal, 2 epochs. And this is on the left, the Hubble images in Iron 2, shows you a beautiful jet emerging from one of these protostars, moving north and south, as a second jet moving to the upper left and a third jet to the upper right. And the proper motions indicate motions of 250 kilometers per second. These flows, by the way, have reached parsec scale dimensions. The image on the right shows that these jets inside this red box have powered shocks completely outside the parent molecular cloud. Now, I want to concentrate on massive stars. That's what we've been working on most recently. So Orion is the nearest site of massive star formation. It produced an explosion. The second nearest site of star formation is the Cepheus A complex, located about 700 parsecs from us. And this is a NICFIPS image we took about 10 years ago, showing you the H in blue, K in green, and near narrowband molecular hydrogen emission 2.12 microns. And after looking at this, we realized there are two massive stars, a 10 solar mass object down here, and a 15 solar mass solar mass object there. And the interpretation is that this is a precessing jet. There's been a series of eruptions every 2,000 years or so, first in an east-west direction, 2,000 years later, slightly rotated to the north. Today, the jet, as measured with the VLA, is along a 45-degree axis. And we see a series of shocks where each eruption has triggered an outburst. We think this is caused by an interacting binary system where the companion in a highly eccentric inclined orbit plunges through the disk, drives that disk into an active phase, drives accretion and outflow, and at the same time, the disk is torqued. Another system 1.3 kiloparsecs away is DR21. It's about 10 times more luminous than Orion, almost 1 million solar luminosities in the central source. And recent ALMA observations have shown that just like Orion, there are Hubble flow streamers indicating that it was an eruption, an explosion, with an energy of 10 to the 49 ergs about 10,000 years ago. But I'm going to concentrate on what I think is currently one of my most interesting targets. It's Sharpless 2 S106, S106 for short. This is a bipolar H2 region, the nearest example of a region which appears to be sliced in half by nearly edge-on accretion disk. In the middle, the source labeled IR is a 22 solar mass central object. We think it's a binary with a point, but a 3 solar mass companion 0.2 AU away. We know this from photometry. What you're seeing here is an H alpha image with Arctic, superposed on a molecular hydrogen image in blue with NICFIPS. And you notice that the central star is obscured by a dark lane. We think there's an edge on disk that shadows the inner part of the nebula, and in fact obscures the central star by about 22 magnitudes. Now, this is the H alpha is quite obscured in the northern lobe. So we went to bracket gamma, which is now shown in a blue light. And in fact, you notice the bipolar symmetry, it's a little bit bent. The northern lobe seems to be deflected to the west, southern lobe to the west as well. Gaia suggests that there may be proper motion at the source toward the east, possibly as a result of an ejection by another star located here called FIR, which is totally embedded. We have multi-epoch Hubble images of this object. And what we've learned is this thing has undergoing remarkable kinematics. It's expanding supersonically with speeds up to 150 kilometers per second. The multi-epoch images, before I get to that, I want to show you the iron 2. The morphology of S106 is unique as far as I can tell in iron 2. Shows a series of intense compact knots. And in fact, when you go to the Hubble images, these compact knots show large proper motions. And I'll show you a pair of images taken 16 years apart, where you can see the proper motions of the southern part of the nebula. You notice that what I call the south bar is stationary. You notice that there are stars in the background. And on this scale, the 16-year baseline of Hubble, the sky is plastic. All the stars exhibit proper motion. So we registered 60 stars to register our images. And with respect to those stars, we measure proper motions, which again exhibit a Hubble-like characteristic. And to show you that, by the way, this is the southern lobe. If you look in the northern lobe, although it's highly extincted, we could recover some of the proper motions. The nebula is moving in the opposite direction with speeds up to 140 kilometers per second. So what's going on here? Well, here's the overall vector field of the proper motions. In the north, they move north. In the south, they move southwest. And on the right, as you see, a plot of the projected distance from the central source and the motions of these various knots. And you notice that the increase rough with a boundary that's linear. Most of the motions that are fast are in the nebular interior, and the motions that are slow are along the edges or at the very ends of the bar. So what's going on here? Well, we think in the case of Orion and possibly S106, the massive star, source I, may have experienced a protostellar merger, because star formation produces very compact groups, multiple systems, and bound clusters or unbound clusters which dissolve rapidly after the cloud is dispersed. Dynamic interactions among stars are relatively common, especially amongst massive stars, which tend to have a high order of multiplicity. We think in Orion, a 4-star interaction resulted in a merger that produced a 15 solar mass central object, source I. However, it could be just disk interactions, which trigger accretion bursts onto the central star, can also produce luminous outbursts with luminosities for massive stars, which can reach 100,000 solar luminosities. By the way, the Orion event was 10 to the 48 ergs 550 years ago. That source would have been a brilliant infrared source in around the year 1475. It's too bad that some monk in Ireland didn't have an infrared observatory. He would have seen probably a bright flare in Orion. So most young stars produce jets. Those jets tend to survive because they're driven by accretion over time scale of 100,000 million years for up to 100,000 to a million years. Outflow signatures from explosions are transient. They disappear within 1,000 to 10,000 years. So even if most massive stars undergo an Orion-like episode, we expect them to be somewhat rare, but they are luminous. In fact, we think with Spitzer, during a monitoring program a few years back, we've detected a number of extragalactic infrared flares, which may in fact be associated with Orion-like events. In fact, I'm using NICFIPS at APO to monitor some nearby galaxies to search for such events. And with that, let me conclude, and you can read my conclusions here, and be happy to answer any questions.
Okay, thank you, John. We have about 30 seconds for a quick question. Anyone wants to jump in here? If not, I'll ask my question, which is I was actually wondering about Gaia, which is you mentioned you actually have some Gaia proper motions for some of the stars, and
Yes.
I'm wondering how many of the stars do you get? Do you just get the brightest stars, and do you expect that to change with future Gaia data releases?
Yeah, so amongst these young stars, of course, especially the massive ones, they tend to be highly embedded. So all our proper motions for the Orion sources, for example, comes from the VLA. It's radio. Most of these young stars emit radio emission, synchrotron, or thermal. And so with long baseline interferometry, we get their proper motions. That's how the source I ejection was detected. By the way, the source X, which is the 3 solar mass star, that we can see in the infrared, although not at visual wavelength. So Gaia's handicapped because most of these stars are still sufficiently embedded to be not in the Gaia catalog.
Okay, yet another reason to have an infrared version of Gaia.
Absolutely.
All right. Okay. Yeah. So I'll go ahead and move on to the next speaker.